Hello, everyone. Welcome to FIG's continuing series of online coach education seminars. Today's topic is related to biomechanics and specifically the coaching biomechanics interface. And biomechanics tends to be a scary topic for coaches, but it is crucially important because it deals with technique. And if you understand the mechanics of a skill, it also informs physical preparation, informs anatomy, physiology, pedagogy, methodology, and so on and so on. So I'm so pleased to be able to introduce our guest speaker for today, Dr. Professor Gareth Irwin from Wales, who can present this topic better than anyone in the world. Gareth was an international gymnast. He was a national coach and manager for Great Britain, for the United Kingdom. He's currently the head of sports exercise biomechanics at Cardiff Metropolitan University. He's the co-director of FIFA's Medical Center of Excellence. And he's the former president of the International Society of Biomechanics and Sport. On top of that, of course, he's published at least 150, I should say, peer-reviewed papers and done international presentations at least 40 times. So Gareth, welcome for this topic. Thank you so very much.
Thank you, Hardy. Thank you for inviting me to give this presentation, and thank you to the FIG Academy for the opportunity to talk about some of the work that I've been doing over the last 2.5 decades, specifically focused on the coaching biomechanics interface.
Super. You know, my preferred topic is biomechanics. I'm looking very much forward to hearing this talk. So I'll turn it over to you.
Thank you, Hardy. And let's start with my presentation. Hello, my name's Professor Gareth Irwin. I'm here today to talk to you about the topic of the coaching biomechanics interface, something that I've been interested in for a number of years, probably nearly 30. And I'd like to start by thanking the FIG Academy for providing me with the opportunity to discuss this topic and particularly make it as meaningful and relevant to the coaching community and to the judging community as possible. On a number of things, four main outlines here. Firstly, what is sports biomechanics? What do we mean by sports biomechanics, and how does it fit into the coaching process? How can it make my process of training as a coach more effective, efficient, and safe? I'm going to provide some examples of what the coach needs to know, potentially, and also what the researcher can contribute to making coaching more effective and helping improve the whole environment and culture of gymnastics so it's safer and the gymnast is at the centre of this process. What do we mean by sports biomechanics? Well, I've taught for about 3 decades on coach education across the UK mostly, and different questions emerge, different worries emerge from coaches that maybe are coaching Olympic gymnasts to coaches that may be coaching 6-year-olds cartwheels once a week. Biomechanics is often viewed as a very maths and physics dominated subject, and at university it is. So why do I need to know this as a coach? How is this going to help me? I already know what a skill looks like, so why do I need to understand about forces and angles, etc.? How does that information help me as a coach? And is this relevant? If I'm teaching kids cartwheels in the gym, is this going to be useful to me? So these are some of the issues that surround the topic of biomechanics within gymnastics and within coaching. And it's been there since the start of sports science, really. So I'm going to hopefully look at this as a topic which and make it as meaningful as possible, which then can be used as a platform to make more objective decisions. So if we look at a definition of the word itself is split or can be split into two. Firstly, bio, which means biology, and we're interested specifically in the musculoskeletal system, the muscles, the structure of our muscles and how they contract and allow our bodies to move, and the neuromuscular system, how that process is controlled. We're also interested in mechanics, the maths and physics of sport. We're interested in things like equipment design, How is the design of this equipment going to influence the forces the athlete is experiencing? How is the stiffness of the bars going to influence the types of movements the gymnast can execute? And also we're interested in the movement patterns, the body positions. What are the best movement patterns to execute techniques safely? How can we reduce injury risk? But the science itself is huge. It ranges from spaceflight biomechanics through to automobile industry, animal biomechanics, and we use all of this information to help us understand and explain the whole role of biology and mechanics in relation to sport. We have these biomechanists at universities across the world, and I work with a lot of them, ranging from the United States to Japan to the Czech Republic, for example. And we run research projects that look at specific questions that we hope are meaningful and have come from coaches or come from national governing bodies. Some examples of these sorts of things include examinations of what are the most effective long swing techniques. So we know in female bars that there are three main techniques: the arch, the straddle, and the pike technique. Which one of these is most effective in terms of developing skills like the catch-up, like dismounts? We're also interested in how skills evolve over time. So, for example, after 1996, at the Olympic Games in Atlanta, bars were permitted to be moved to 1.8 meters apart. So gymnasts were more freely able to swing. So skills like the inward and outward catch-up emerged. And questions around which one of these techniques is the most effective. Which one of these techniques will allow me to potentially produce a straight catch-up that the men were already performing. So other skills like the toe-on catch-up was started to be developed. Followed by the toe-on straight catch-up. So the biomechanist can come in and say which of these techniques is most effective, which of these techniques will produce the outcomes of being able to produce straight catch-ups, helping to reduce injury and improve performance. And this information is then disseminated to the governing bodies or disseminated into scientific journals. One of the key areas that we're researching at the moment is the influence of injury risk, and how does, for example, landing strategy, landing technique, the movement patterns and body positions that we adopt during that landing, how does that influence injury risk? We know in males and female gymnastics the rules are different. Females can land with their feet together, or have to land with their feet together, and males can land with their feet apart as long as their heels can touch. Do these differences produce effects that may increase or influence injury risk? So these are very interesting and very meaningful questions. But I think the disconnect that we see within biomechanics is the fact that we find it difficult as coaches, and I was a coach a long time ago, and I was a bad gymnast a long time ago. How does it fit into, how does biomechanics fit into the coaching process? How can we make training more effective and efficient and safe by understanding this? Not just at the elite level, not just at the advanced level, and not just in artistic gymnastics, but across all gymnastic disciplines, but also at the recreational level, at the mass participation level. So let's look at gymnastics, for example, and let's look at how we can compartmentalize it. We've got the skill, for example, catch-ups, round-offs. We've got phases of skills like takeoffs, landings. What techniques are there that the performer has to perform or performs in order to achieve these skills? What do those techniques look like? What are the movement patterns that the performers achieve in order to be successful? Ultimately, how do those movement patterns work? What is it that makes the skill work? And I think as a coach, that's the key question. How does the skill work? How does this technique work? And if I can understand that, how can I then develop that in my athlete? How can I develop these shapes, these movement patterns that produce the outcome that I'm trying to achieve, whether that be a kazamatsu on vault or whether that be a catch-up on A-bars? How do I ensure then, once I've got that technique, that they're robust, that they're consistent, that they're safe, and that they can cope with different environments, whether that be competing in a village hall or competing at an Olympic stadium? And how do I maintain these techniques as the gymnast is growing, as the gymnast is changing their morphology, and how do I maintain that throughout a season, throughout a career? Ultimately, what I think I'm trying to do as a coach is make my gymnast as safe, adaptable, innovative and dynamic as possible, with safety being the first part of that process. So I'd like to introduce a new concept to you, which potentially you've heard of before, and that's called the constraints-led approach in gymnastics. And really that's focused on, as coaches, when we look at preparing, nurturing, developing our athletes and making them as robust, adaptive, innovative, self-aware and stable as possible, with programs that are individualized, that are safe, effective and efficient. We really need to take into account three things that impact on the performance of the output goal of gymnastics, i.e. to achieve the skill that we're trying to achieve. The three constraints include the individual, i.e. the gymnast themselves, their physiology, their psychology, to a certain extent their sociology, the environment in which I'm training or competing, whether that be a village hall, an international Olympic arena or some other venue, and the techniques that I've got available to me to achieve the overall goal of the skill I'm trying to produce. These three things, the individual, environment and task, have an interactive effect over the performer. So when we look at trying to achieve the movement goal, which is dictated by the international governing body in gymnastics and is present in our code of points, we know what shapes and movement patterns we're permitted. So the techniques to achieve that and the effective techniques to achieve that are probably quite well known. Those that are more effective though, that's the art of coaching. We need to take into account the individual in terms of their age, their sex, their growth and development, and also very importantly their mental well-being. And also we need to take into account the environment, the training environment, the competition environment, whether that be for recreational, mass participation gymnastics or Olympic gymnastics. From these three interactive components, constraints, the gymnasts produce the movement patterns that they are using to achieve the techniques. They coordinate their body in terms of how the joints are interacting. There's a level of variation. We need that variation to be able to adapt to training, for example, on a podium or competing in an arena or competing in a gym that we're not particularly familiar with. That variation gives us a stability in our performance. What this process does is it improves our understanding of technique, it reduces the injury risk, it helps us with skill development and physical preparation selection, and that's what I'm going to talk about a little bit more now. So from a coaching perspective, how can this information about the task, the technique, the environment and the individual help me as a coach in the gym when I'm teaching 6-year-old cartwheels on a Monday afternoon? So how does this knowledge help coach? Well, let's look at where we get this knowledge from. If we go into the gym and I set you the challenge of developing cartwheels, I don't know why I keep using cartwheels to a group of 10-year-olds, then you'll initially, as a coach, think, okay, what are the drills or what are the progressions I already know? And I'm going to modify these to the individual athlete. I already come to this situation with a level of current coaching knowledge. That's come from resources. You may have been an ex-performer, you may have been on coaching courses, your child may be involved in gymnastics and you're just joining in because you don't want to sit there and wait for them to finish their session. We develop a mental picture of the skill. So if I was to ask you to describe this cartwheel, you'd think about the shapes and movement patterns. You may see an image, you may see this as a strobed picture, you may just see a black and white photo in your head of what a cartwheel looks like. So you'll understand what the skill is. But you'll also have some knowledge of the difficult parts of the skill, the bits of the skill that make the skill work. And this is the biomechanics. You might not have the terminology, but you'll have, from a coaching perspective, the understanding of what the key parts are. And this is a very descriptive type of understanding. The last two here are really helped by observation of elite performers. And with things like YouTube and with things like the access to social media now, we have a lot more of this information. What this process, what these four themes do, is that they develop this conceptual understanding of what skill is, of what the techniques are, this mindset of what makes up a skill. The quality and the accuracy of that mindset would dictate the ultimate ability to achieve the skill. So your ability to understand the task will have a huge influence over the drills or the progressions or the physical preparation that you do. So from this mindset, we start to identify what the key technical aspects of the skill are. What are the key phases, and how can we break the skill down? A nice example of that comes from high bar. Here's a gymnast performing a long swing. Starts in the top left hand corner and rotates around back to handstand in the top right hand corner. Now we know, and most coaches will know, that there's a phase in this skill that allows the gymnast to overcome gravity pulling them down on the other side of the swing. Now this phase happens when the shoulders move from a hyperflexion to extension and the hips move from an extension to flexion position during the under phase of the movement, this arch to dish movement. What we know from biomechanics is that during this phase, which happens just after the vertical, 70% of the musculoskeletal work that the gymnast does occurs in this phase. In elite gymnasts, 2/3 of that work come from the shoulder. So knowing this, knowing that that phase is important, so I would hazard to guess that most coaches would identify that that's a key phase, and it now being supported by biomechanics suggests that that phase should be part of or incorporated in our training. So we replicate those key characteristics of the final skill, of the long swing in this case, in the drills that we're choosing. So we're replicating those stresses, those biological stresses on the performer, and that allows the athlete to adapt in an effective and efficient way. So for example, if we take the long swing and we look at this phase called the functional phase, where the gymnast goes from an arch to a dish at the hips and at the shoulders, and then we look at how that is replicated within the different progressions that are being used, we can start to see or identify which progressions are going to be more effective and which progressions are going to be more efficient. So we could take all of the progressions that are used for developing the long swing on high bar, and there's some that perhaps people wouldn't use nowadays. But understanding that this key phase is fundamental and needs to be replicated in the strength and conditioning exercises that we do allows us to be more effective as coaches. So replicating those key phases allows us to develop the physical preparatory activity, develop the gymnastic skills, and then that provides a feedback loop back into your current coaching knowledge. What this model presents, and there are papers that I'm sure that I can provide to you that support this. This represents not just this idea of bridging the gap between what the biomechanists do and what the coaches need to know. It makes it much more of an interface. That the language we're talking about in terms of shapes and movement patterns, these are the sorts of language that we're using when we're coaching athletes. So we're starting to share a more common language. So to clarify how this helps, it helps us understand the underlying causes of movement. How does the gymnast reverse their rotation up to the point of release so that they can rotate and catch the bar again? How does the gymnast initiate the rotation during a forward roll to allow them to actually stand up out of the forward roll? What is it about this pushing phase that allows them to do that? And we can design our drills and progressions and physical preparation around that. So allowing us to understand the movement patterns of the technique is important, but what also the biomechanics provides us with, and this understanding of the constraints-led approach, is that it allows us to understand the musculoskeletal demand of the movement. It can inform us in terms of the training principles, i.e. overload and specificity, and how to best overload our gymnasts so that their adaptation occurs in the most safe and effective way. That informs our skill development. It allows us to select the progressions that are going to be best for that gymnast and for also for that specific skill. It's key then for information around strength and conditioning and physical preparation of our athletes. And it allows us to combine both the coaching knowledge that we already have with some scientific understanding to drive this technique selection. What's the best techniques for certain individuals? We can then use that to inform the training drills that we use to develop those skills. We can design skill development programs that are more effective and efficient because we can start to identify the progressions that replicate those key phases. And then that can inform our physical preparation, and it can make the stresses on the performer, both physical and psychological, more effective, and safer. So this overall sharing of a common language, this integration of biomechanics and scientific understanding in general, is really just part of what a coach is. I'm going to move on to some specific examples now, and one of those examples is going to come from floor and one of those examples is going to come from vault, and I'm just going to touch on some of the underlying principles that we have in terms of understanding skill. So the first, we're going to look at a very simple forward somersault on floor. The gymnast takes off in the left in a leaning slightly forward position, takes off, performs the skill, rotates through 360 degrees and lands. I admit it's just a stick figure diagram, so don't criticise it too much. But there are certain things we need to know. Once the gymnast is airborne and has left the floor, they rotate around a point called their centre of mass. This centre of mass is around about where the hips are, and it represents all the mass of the body. We rotate around our centre of mass when we're not in contact with something. Once we've left the floor, the magnitude of rotation that we have is set. That won't change. The only thing we can change as performers is the moment of inertia, that resistance to movement. So we know during a tuck somersault, when we're tucked up into a tuck position, the rate of rotation increases. It allows us to rotate through that 360 degrees safely before we start to open out, increase our resistance to rotation and land again. So that rate of rotation, that resistance to motion, because we spread our bodies out, we make ourselves longer or shorter, is all down to how much rotational capacity we have at the point of takeoff. So that's the key bit. The key bit to the whole success of this skill is based on the magnitude of rotation you can generate at takeoff. And then you can manipulate your body position during the aerial phase to perform the skill successfully. So there are three things there: the magnitude of rotation, the resistance to rotation, you're more resistant to rotation when you're in a long position, and the rate at which you're rotating. And you rotate slower when you're in a long position. And look at a gymnast performing a straight example. When they're in the straight position, they're going to rotate slower than they are than if they were in a tuck position. We also know that the moment of inertia is going to be higher, that resistance to motion. So because of that, because we want to be in this straight position, we know that the amount of rotational capacity, the amount of momentum we need to produce at takeoff is going to be higher. So again, the key part to the generation of this rotation is what happens at takeoff. And the gymnast then can manipulate their body position in space during the aerial phase to execute the skill successfully. So when we look at the somersaulting rotation on the left hand side during this aerial phase, the tuck position is easier to rotate than in the straight position. If we want to have the option of doing straight somersaults, we need to produce enough rotation at takeoff in order to allow us to perform that skill, with the knowledge that during that aerial phase that magnitude of rotation doesn't change. The only thing I can change is the rate at which I'm spinning, the rate at which I'm somersaulting, and the shape of my body. We could have talked about the creation or the factors that influence the creation of that rotation, i.e. the amount of force I apply to the floor, the direction of that force, my angle of lean, and how that influences this magnitude of rotation. Whether running up to the performance, what influence that horizontal velocity has to this. So these are all important things that we need to consider when we're looking at something as simple as a forward somersault. But in terms of controlling the somersault rotation, this manipulation of our body shape, which controls the rate at which we spin, is the fundamental component. Let's look at another apparatus, the vault. The vault has obviously evolved over time. We've now got a vaulting table, which is about 1 metre square, slightly angled, probably more elastic than the original vaulting horse. And understanding some of the key aspects, and I'm just going to touch on one or two, I'm certainly not going to do an in-depth analysis of the vault, is really important to be able to identify what aspects or components our gymnasts are struggling with, where to focus our physical preparation, and how better to understand skills. So let's have a look at a handspring front somersault and a handspring double front somersault vault. Here we have a strobed image of Dragulescu performing. He's got his hands on the vault here in the top right hand corner, tucks into the air, he does his 2 somersaults, then does a half turn, performs a Dragulescu, and then lands successfully. If we compare the time that he spends in the air between a handspring front somersault and a Roche vault, they're very similar. The height of the 2 vaults is different, but the most important variable, or one of the most important variables, is the rate at which that rotation is occurring. So the angular motion is a fundamental component, a fundamental part of the aerial phase. The trajectory obviously of the performer is, but that unless you have produced the right angular momentum, the right angular capacity to rotate at the point of takeoff, then it would be very difficult to be successful. This rotational capacity comes from what happens before the aerial phase, so the vault contact phase. And during the vault contact phase, on the right here with the big red arrows, you can see that the gymnast, as he attacks the vault, as he hits the vault with his hands, there's a large horizontal force and a slightly lower vertical force. Nearly 2/3 of the force that the gymnast is experiencing at this time is horizontal. As well as those 2 forces, he's got angular motion rotating around the point of application now, the hands, that's helping generate the angular motion that he'll have eventually in the aerial phase. At the point of takeoff, with the yellow line, you've now got a vertical speed and a horizontal speed, or vertical velocity and horizontal velocity, as well as rotational capacity. Being able to maintain the rotation from touchdown to takeoff is one of the key indicators of successful vaulting. If the momentum, if the angular motion reduces between this point and this point, touchdown and takeoff, the resulting aerial phase angular motion around the centre of mass will be reduced. But where does that come from? Well, that comes from what happens at the springboard. So when the gymnast lands on the springboard, there's a large vertical and horizontal force he's applying, in this case, through the springboard. And interestingly, when he hits the board in that initial phase, the angular motion is going the other way, as the gymnast's feet travel slightly forward of their hips. At the takeoff then, he's got a vertical and horizontal speed and angular motion, and in fact this early braking of his horizontal speed during the run-up is the thing that creates this vertical and horizontal velocity and then subsequent motion after. So key to it all then is the approach run. What happens during the approach run? Now, running up to the vault isn't as simple as just running in a straight line. We've got the targeting that the gymnast has to do to the springboard. We've got the other technical characteristics of hand placement, etc., that we've just seen in order to maintain that momentum during the touchdown to takeoff phase at the board and the vault and the horse. But we know during sprinting and during running there are two key variables that are associated with successful sprinting, and those are step length and step frequency. The length of my steps and the rate at which I'm doing them will dictate how fast I go. And ultimately it's that horizontal speed, that horizontal velocity, that's the most important thing. And interestingly, there was a number of studies that looked at how fast gymnasts actually run. And here's a little graph of, on the bottom, we've got distance, so 0 meters in the bottom left to 100 meters on the bottom right. And on the vertical axis, we've got the velocity of the performer. And what I've done is I've actually plotted two international sprinters, Fraser, who ran 100 meters in 10.73 seconds, and Usain Bolt, who at this point in time had run 100 meters in 9.58 seconds. How do males and female gymnasts compare to these sorts of speeds? Well, if you look at 25 meters into the run-up, you can see that males are running around about 9.6 to 9.7 meters per second, and females generally, depending on the vault of course, are running around about 8.2 to 8.3 meters per second. So we can start to look at what are the most effective run-up velocities for our performers. So we can then design drills and progressions that are specific to those characteristics. So really what I wanted to do today was not go into too much detail about the mechanics of skills, about the fundamental principles. What I wanted to do is give you a context of how biomechanics fits into the coaching process, how you can use biomechanics. And some of the take-home messages are, firstly, it allows us as coaches to develop this conceptual understanding, this mindset of how a skill works, that the dish to arch during swinging is important. It allows us to appreciate the forces that the performer is experiencing. So where are these big loads happening? For example, on rings, when the gymnast is hanging, we know that the rotator cuff and the musculature around the shoulder joint is what's holding the gymnast in place. So physical preparation around that joint, rehab or prehab around that joint is fundamental. It removes the trial and error method of training. It reduces the time spent teaching skills and makes the process of overloading the athlete more effective and efficient. Ultimately, what biomechanics and also what sports science can do is it can make you a better analyzer of human movement. It can make you make decisions that are more objective about the direction in which you want the performer to go. So it's key to understanding technique. It tells me how the skill works. This interaction of the task, the individual, the environment in which I'm about to perform allows me to make a much more individualized approach, a much more gymnast-centered approach. The well-being of the gymnast then becomes the central part of that. Linking biomechanics to the training principles allows us to replicate those key phases in the skill and put them into the progressions to make skill development more effective, efficient and safe. We know coaching at all levels is a multi-dimensional role, and biomechanics plays a key part in that role. It explains movement and is the foundation of how we as coaches can inform the decisions about those movements. Thank you very much.
So I think the thank you, Gareth, is all from us. Thank you so very much for this fascinating presentation. As always, I think biomechanics has many questions. So the guests we have today are representing Rhythmic Gymnastics, Katie Sigsworth from Australia. Welcome. Katie is a former top gymnast for Australia, top rhythmic gymnast, winning silver medal at the Commonwealth Games. She has coached for 26 years at the national and international level. She's also a national judge for the past 26 years and has devoted the last 10 years of her life to coaching or to coach education in rhythmic gymnastics. Among that includes teaching several of the FIG academies. And then we have also privileged to have Jeff Thomson from Canada. Jeff was a coach of many of Canada's top male and female gymnasts over the last 20 years or so. He's currently the chairman of Gymnastics Canada, chairman of the board of directors of Gymnastics Canada. And he's also currently on the FIG Men's Technical Committee. So welcome both of you. I'd now like to ask Katie to ask one or two questions, and then followed by Jeff asking Gareth one or two questions.
Thank you, Hardy, and thank you, Gareth. It was actually a fantastic presentation and really insightful. I have quite an inquisitive mind and I love the science of our sport. And as Hardy said, I come from rhythmic gymnastics. So there's a lot more biomechanics needed, I think, in the study of rhythmic gymnastics and how we can improve and educate coaches and athletes in this area. So one of my questions I would like to ask is, how can we better use biomechanics in the club level as well as the elite level in improving our sport?
I think an important component to this is the working relationship between kind of the national governing bodies and the universities, and potentially in Australia the AIS, I guess, with your system. There isn't much biomechanics research that's been done on specifically skills within rhythmic gymnastics for a number of reasons. And I think it's an engagement process both within the coaching community and within the scientific community. So if there are specific questions, for example, there may be different styles of throwing and catching. There may be different kind of timings related to rolling and catching, these sorts of things. And I'm not a rhythmic gymnastics coach, so I apologize if I've just simplified your entire sport. But those sorts of things, understanding and describing the techniques to start with, explaining how they're developed, I think it just comes from a desire within the sport itself and within the scientific community. So there are certainly a lot of excellent biomechanists and sports scientists in Australia, and that would be more than happy to engage with addressing questions that would be meaningful at the elite end, and also then at the coach education end, you know, the helping you understand what performance looks like, how performance works, what are those mechanisms of, you know, throwing, for example. There's some classic literature in throwing about sequential movement, how the shoulders, elbow, wrist contribute to the development of throwing and catching and landing. You know, there's some really interesting questions that could be done within rhythmic gymnastics that could inform how the developing coaches understand the sport. You know, you being an ex-performer, understanding those techniques tacitly gives you such an advantage. Being able to translate that into a kind of coaching scientific biomechanics interface approach, yeah, it's partly engagement, and partly the you know, the scientists as well need to reach out to the clubs to see what there is, what questions need to be addressed.
Thank you. That's wonderful, and I think that we'll definitely be taking that up. We certainly work well with the AIS here, and have had a number of interactions at some of our national camps. So we'll definitely continue that relationship, because I do love the science of the sport, and I think it's really important, which leads me into the next question I had for you, which is in regards to how biomechanics impacts the health and well-being of athletes. So, you know, it's not just the technical skills in terms of the science of this, but it actually leads into the health and well-being. I guess I would ask you to talk some more about that.
It's a great question, Katie, and particularly pertinent at the moment with gymnastics being under the global spotlight in terms of well-being of gymnasts, the environment and the culture of gymnastics. Certainly when we look at developing gymnasts, you know, we've got a responsibility to understand the physical load that we're exposing them to, not necessarily the big massive loads of landing, but this accumulative load. And also there's a need to understand how that impacts on mental health as well. So are there periods of the day or periods of the competitive season when certain stresses and anxieties are high, that loading will have a detrimental effect both on the physiological and the psychological characteristics of performers? Within female gymnastics, you've also got the issues of things like menarche, you know, puberty. You've got things around maturation, growth and development across all gymnastic disciplines. So I think biomechanics needs to work together with physiology and psychology to understand and better explain how we can, in a very sensitive and meaningful way, look at growth and development and loading of performers to allow us to come up with recommendations which will ultimately make the environment safer and more inclusive. And I think, you know, where that's dropped off, where that's not happened, that's where working too hard, overloading performers physically hasn't been at the betterment of the gymnast or the sport. So yeah, I think, you know, biomechanics has a role to play in that. There's lots of research in this now. Other sports, soccer, I'm involved in rugby projects where we're looking at cumulative load. And, you know, gymnastics has got an opportunity now to really engage with this and lead the way in terms of protecting its athletes, in terms of the well-being, physiological well-being, psychological well-being, and the interaction of all of these things. And it's this interdisciplinary approach that's the key to it, and not just having a biomechanist say this and a psychologist say this and a physiologist say something. It's how we interact together to address questions. That's the answer.
Thank you. That was a fantastic answer. I'm really excited by biomechanics and its place in our sport, in rhythmic gymnastics.
Thank you very much, Gareth. As you know, I just love this area of biomechanics, and in many ways, I feel like I've come full circle being on this session. As you know, I had the pleasure of working under Hardy for many, many years as kind of an apprentice coach, if you will, and he has his graduate degree in biomechanics. So biomechanics literally informed my coaching right from the beginning. I mean, I took what limited gymnastics experience I had myself, and because of that biomechanical background that Hardy instilled in me, and our coaching education program instilled in me, kind of right from the very, very beginning, I think I enjoyed a relatively successful coaching career because everything was based around, you know, what needs to happen from the perspective of physics, and really movement is physics. But that leads me to my first question, which is something I've always struggled with, having traveled and seen different techniques in different parts of the world. Is there an ideal model in your point of view from the point of biomechanical and physics point of view? Thank you.
Thank you, Jeff, for your question. It's a really interesting question, and I think gymnastics stands amongst a certain number of sports where the movement patterns and body positions that we try to perform are kind of dictated to us. You know, a crucifix cross on rings, your arms have to be at 90 degrees, turning, twisting. You know, the fact that we're dictated in terms of some of those movement patterns, it adds to the answer that I'm going to give now. The answer is there is no model performance. There's no model technique, and we need to be able to adapt our technique based on, as I said before, the environment that we're in and our own individual capacity as a biological entity, you know, psychologically, physiologically. So you and I may perform, let's say, a Ketchev on high bar, but we would go through maybe the similar shapes and movement patterns, but how we achieve that would be very different because of our differences in morphology. And that's where our body's shape and size, and that's where coaches need to think about how to, on an individual level, find the technique for that person. And so the triangle that I presented of constraints, that process happens naturally. Our bodies are massively able to seek out the right movement patterns to achieve a skill. And, you know, and you can see this in kind of things like parkour, for example, where technique isn't as regimented as it is in maybe artistic gymnastics. These techniques emerge, and they emerge around the individual's ability based on those physiological, psychological characteristics, and that self-organization becomes quite prevalent. I think it's quite dangerous to think about. I think there are dictates of performance. So you have to create angular momentum, rotational capacity if you want to perform a triple somersault on floor. There's no question about it. You need to reduce your moment of inertia if you want to do more than 2 or 3 somersaults. You know, these things are mechanical laws, but how we achieve that it's important that we recognize the individual difference of our athletes and allow them to perform it in different ways.
Thank you very much, Gareth, and I really appreciate what you're saying, and I certainly found that within my own coaching. I had to adjust really significantly for the body types for the situation I found myself in. My second question relates now to the area I'm most involved in, of course, which is in the judging side. I'm on the FIG Men's Technical Committee. So there's really 2 parts to this question. The first one is, do you see a role in biomechanics in terms of assessing the difficulties that we award to an element or a skill in the code of points? And then the second one is, do you see a role in biomechanics as a possible tool for the awarding of let's say, bonus points for virtuous levels of performance, a way to give back to the gymnasts, to those gymnasts who do a skill in an exemplary way, for example, much more height, a greater exhibition of angular momentum, et cetera, et cetera. So the sort of a 2-part question for you: the assessment of difficulty, and then the assessment of potential bonus points for exceptional performances.
That's a really interesting question, Jeff, and a really difficult question, to be honest, to answer. But I'll have a go, and it's something that I have thought about in the past. So the first part was about how biomechanics can be used to assess difficulty, and you know, and I guess some of the work we did with Ketchev was around that. You know, inward and outward facing Ketchevs. We know that if there are certain loads on the performer, certain musculoskeletal loads that the performer has to achieve, and they change as a function of the skill, you could suggest that that skill is more difficult. You could suggest that if the angular momentum requirement of a straight Ketchev or a full twisting Ketchev is significantly different, then they need to be in different categories. So I think you could look at the code of points, and let's take floor, for example, and go and let's say tuck back, double tuck back, triple pike back. And if I looked at female gymnastics, I'm not sure that they would be in the same, that might be B, C, D, F, G. A double tuck and a double tuck in female and male gymnastics might not be the same category. I'm not 100% sure whether that's true anymore. But what you could do is you could say, okay, is the difference between a double tuck and a double pike actually the same as the difference between a double pike and a double straight? So is it twice as difficult to do something in a straight position where we know the moment of inertia is higher, the resistance to that rotation is higher? So we could use biomechanics and some very simple biomechanical variables like capacity to rotate to categorize skills and say, yeah, this is why this is a D, and this is why this is a B, and this is the why this then is a C, because it's kind of not really a D yet, but it's more than a B. And you could do that from in strength moves, you could do that in twisting moves, and it could be a nice review and contribution to gymnastics. It also then gives some more objective kind of rationale for the classification of skills. And I know, you on the FIG committees do a tremendous job of, a very caring job of how to organize and manage the code of points. And it may be a tool that could be used to help that. The virtuosity one is a brilliant one. I think that's, you've got, two examples of gymnasts in across all the disciplines doing the same skill, one of them going a meter higher than the other. Let's just say tuck back somersault, opening out early and having the capacity to rotate in the second part of it in a more straight position. We used to see it in the sets, didn't we, a lot when there were compulsory exercises, there were virtuous performances. You go back years and you used to have, I think it was COV, courage, originality, and risk, or something like this. And so you could have the assessment of two of the same skill, and somebody that's able to create more velocity at takeoff, that's able to have more time in the air, that's maybe able to create more angular momentum, they could score more than somebody that wasn't. So, I mean, trampolining does that to a certain extent with flight time. And there are technologies now that could be used to assess that. I know that markerless motion capture has been used in a gymnastics setting. There's a lot of research to go on around that. Although we need to be careful about using some technologies. I think it's certainly an area that I would suggest that the FIG should be looking at in terms of, are there metrics that we can use that again help us, as Katie said, help us with the well-being of the athlete, because we're able to have some scientific objective measure of performance put back into the sport.
Thank you very much, Gareth, for those thoughtful responses. And thank you also for your comments towards the technical committees thinking deeply about the difficulty. We really do. I have to say that the amount of time and energy and discourse that we go through before we assess the difficulty is very comprehensive. So I appreciate that comment. Yeah, it was interesting. Even again at this Olympic Games, I was struck by the need to somehow reward gymnasts for those exceptional performances. There was some skills that were done without deduction from a purely artistic, let's say, or even technical point of view. Legs were together, toes were pointed, and so no deductions. And then the next gymnast comes along and does the same skill, but with this increased elevation, and you go, how can we give that gymnast some benefit, some reward for doing that? And I think it may help push us in the direction a little bit of saying, I can do a simpler skill, which is therefore safer to some degree, and get more points than trying something more difficult, which is inherently more dangerous and has a greater risk of failure. And it's something I've really been thinking about a lot lately, and I've talked to the technical committee about, and I think it would be interesting to engage with you on that, to see if there's some work that we could do to bring back this positive form of scoring to gymnastics.
Yeah, I completely agree, Jeff. And I'm always open to being involved in anything related to gymnastics, and this is something that's close to my heart. I think an interesting, and I know that We spoke about this when we presented a couple of years ago. There's a group in Japan, Toshi Fujihara at the University of Osaka, worked with Pierre Gervais from the University of Alberta on assessing double leg circles, and looking at the level of extension, the level of straightness in the circle, using a markerless motion capture system. And it was set up in his gym, so the gymnast could finish their routine and go back to the iPad and see the level of extension throughout their whole sequence. And those sorts of technologies, those sorts of, because as well as I do, if you've got a gymnast circling on pommel, somebody with a McGillney type of execution is going to have a very much virtuous performance, and those sorts of technologies are available, and it could help coaching, it could help judging, and it can help the environment itself. So I think there's a lot of really exciting stuff to do, and I think gymnastics is at that point in time where technology is now at a level that if we can engage with the scientists, the national, international governing bodies, the coaches, we could do some really meaningful work.
That was absolutely wonderful. Thank you, Gareth, for that presentation. I think the questions brought out a bunch of additional detail and for understanding. I especially appreciated Gareth's comment on the interdisciplinary nature of our sports sciences, how we should work together. And of course, that's what the Academy program has attempted to do to some extent. So it remains only to thank the viewers for watching this seminar, to thank Gareth and Jeff and Katie for their participation. And of course, this wouldn't be possible without the efforts of the FIG Education Commission. So thank you very much. And especially the huge amount of work done by the FIG staff in the background to make these things possible. For the viewers, please follow our future presentations, always on the FIG YouTube channel. And if you wish, look at the past 20 or so that we have done. Thank you. All the best.